And I believe with that we are live. Let's go ahead and check. Can I see my hand? Yes, I can. And can I hear my voice? And that's also a yes. All right, time to put away the headset. And let's see what we want to do for today. I was thinking of doing momentum, so let's go ahead and open the momentum chapter in my book and see if we can pick any good problems, and let's just get right to it. Need to get my mind off of something I've learned about Twitch, which is the fact that apparently I can't upload videos unless I become an affiliate or a partner, which is something I never even planned on doing in the first place. So yeah, that has me a bit miffed. Especially because I had some issues with my last gaming stream, and I thought it would be a simple fix of just stitching together the two parts and uploading that as a video, but that's not happening, so it is what it is. I guess I could always just upload that stuff to YouTube, but if that's going to be the case, then why bother streaming on Twitch in the first place? Let's see, where do I want to start? Well, this is a very common problem that gives people a lot of trouble. So this one says we've got ourselves a wall. That's not a very straight line that I drew. That's a little bit better. And along this wall we have an object. It's a 3 kilogram steel ball. It strikes a massive wall at 10 meters per second at an angle of 60 degrees with the plane of the wall, and it bounces off the wall with the same speed and angle. If the ball is in contact with the wall for 0.2 seconds, what is the average force exerted by the wall on the ball? So the ball comes in something like this. And that right there is a 60-degree angle. And the ball bounces off also at a 60-degree angle. Let's see if I can draw it well. Yeah, that looks about right. Oh, and I guess I should comment for those who didn't see the video I uploaded previously. I've made some improvements to the sound, as you can hear, so I guess I don't have to make my voice louder than it needs to be anymore. I learned how to use the gain filter on OBS, so hopefully this will spare my throat a little bit, and maybe I won't be as exhausted after these streams anymore. Anyway, we had the ball goes in at a speed of 10 meters per second, bounces back off at a speed of 10 meters per second, and also at a 60-degree angle there. I think I drew that arrow wrong. It's tilted a little bit too high up, but you get what this is supposed to represent. So it's asking what's the average force exerted by the wall on the ball. And if you remember the impulse momentum theorem, then you know that the impulse, which is defined as force times change in time, is equal to the momentum. The impulse momentum theorem is equal to the change in momentum, rather, is equal to the change in momentum. Okay, that's all good, but here's the part where students tend to screw up. What is the change in momentum of this object? If its mass is 3 kilograms, and it has an initial speed of 10 meters per second, and a final speed of also 10 meters per second. I drew the slash in the wrong place. Let me actually just cross that out and rewrite the whole thing. 10 meters per second. There. A lot of students here will say that the change in momentum is 0 because it's 3 kilograms times 10 meters per second before and 3 kilograms times 10 meters per second after. This is wrong because momentum is a vector. To calculate change in momentum, you have to account for both change in magnitude and change in direction. You have to account for both of those factors. Change in momentum equals momentum final minus momentum initial. This is vector subtraction. So momentum final minus momentum initial. Momentum final is like that. And then minus momentum initial is the same as adding the negative of this. If momentum initial is up and to the right, then negative momentum initial is down and to the left. And momentum final minus momentum initial would then be that value. Momentum final minus momentum initial would have to be that vector pointing all the way to the left. Very, very easy mistake for students to make. I see this all the time. Remember, momentum's a vector. Okay, so that means we need to take a look at the components. At least that's one way of looking at it. We could also solve this geometrically, just doing triangle stuff. But when in doubt, components are the way to go. So I can do change in momentum in the x direction equals momentum in x final minus momentum in x initial, and change in momentum in the y direction is momentum y final minus momentum y initial. And of course I can put the arrowheads on top if we want to be nitpicky about it. Okay, what are the x and y components of each of these momentum vectors? Well, we know that this angle is 60 degrees, so we can say the cosine component will be the vertical component because that's the adjacent side to the 60 degrees, and the sine component will be the horizontal. So for momentum in the y direction, for this one it's going to be 10 times cosine of 60 in the upward direction, and for the final momentum, well, I guess I'm doing the velocity rather than the momentum, but yeah, let's multiply the mass in. So If you multiply in the mass, then the total momentum is 30 here and 30 here in magnitude. So 30 cosine 60, I guess I'm doing the y's first, change in momentum y, equals, for momentum final, it would be 30 cosine of 60, and in the upward direction, so positive, minus, for the initial momentum, it would be also 30 cosine of 60, and also upward, so minus positive 30 cosine 60, change in vertical momentum is 0. That shouldn't come across as a surprise, especially when you consider this drawing that we got. Also, it shouldn't come as a surprise because the wall isn't going to exert a vertical force on this object. It can only exert a horizontal force. I guess if the object stuck onto it long enough that it could slide against the wall, then you could have had friction, but considering how quickly this all happens, I think even then common sense would suggest that this wall is not going to exert any vertical force. And with no vertical force, you can't have a vertical change in momentum. Okay, so that's that part cleared. And then for change in momentum in the x direction, here we are going to have a difference because this one is going to have momentum in the x direction that points to the right. And then for the final momentum, it's going to be momentum in x pointing to the left. And if I do left minus right, that's the same as left plus left. So let's go ahead and see. I guess I'll write it down here. Change in momentum in the x direction equals, for momentum final, I guess I'll define left as negative here, is negative, we said the momentum was 30 kilogram meters per second times sine of 60. And then minus momentum in the x initial is going to be positive 30 sine of 60, since the initial x component of the momentum was to the right. So negative minus positive gives you negative 2 times 30 sine of 60, and the rest is just calculator work from there. So negative 2 times 30 times sine of 60 degrees is negative 30 root 3. I would appreciate it if this calculator would stop simplifying things to roots. Equals negative 51.96. Okay, and the meaning of the negative is just that it's to the left, so we can actually drop it. We can just say 51.96. Wait, did I say meters per second? Kilogram meters per second. Let me rewrite that. Kilogram meters per second to the, did I say right, to the left. So we can call this 51.96 kilogram meters per second to the left. Okay, but the original question was to calculate the average force exerted by the wall on the ball. And they said that the contact time with the wall was only 0.2 seconds, so that's our delta t. And from here the rest is easy, so just do force times delta T, average force times delta T equals our delta P. Average force times 0.2 seconds is equal to 51.96 or negative 51.96 if you prefer. And then if you divide by 0.2, 51.96 divided by 0.2 gives me 259.8. So the force is 259.8 newtons to the left. To the left. And is that visible? Not quite. There we go. So yeah, if you decided to keep the negative here, you would have gotten negative 259.8, which would mean the same thing. It's all just a matter of personal preference and how you choose to define your coordinates and whatnot. But my preference is use positives and negatives temporarily as intermediate steps when trying to calculate things, especially when you can't predict with high confidence what direction a vector will take at the end. But once you're done using your positives and negatives for that, I would just recommend to then take the magnitude, drop all usage of signs, and just take the magnitude and write out the direction in words. Especially because positive and negative only works when you have two possible directions. And in two-dimensional problems, you have, well, an infinite number of possible directions, a whole 360-degree range. So I would not count on being able to rely on positives and negatives forever. Get used to describing directions in words. With, I guess, angles when they're needed. That takes care of that problem. What can I do next? I guess we're jumping straight into conservation of momentum problems, because all these other ones look too basic. I mean, it would be one thing if I expected the target audience for this session to be complete beginners at momentum, but this is really supposed to be a review for the AP students especially. Okay, here's one, number 21 in my book. And in case you're wondering which book I'm using, I am using, I guess I can just show it to you. I'm using, yet again, College Physics by Serway and Fawn. I use this book a lot, especially for algebra-based physics. For calculus-based physics, I use a different book, although I still use this book even for the calculus-based students, because I find that the best way to teach calculus-based physics is to teach things algebra-based first and then add the calculus on later. Because when you teach students calculus-based techniques in tandem with algebra-based techniques, they'll try to use calculus on everything. And if you do algebra first, then they can really get a sense of how far algebra can take them, so that they only think of using calculus when it's actually needed. But that's enough educational philosophy from me. So it says a 45 kilogram girl is standing on a 150 kilogram plank. $150 kilogram plank. And they said the girl was 45 kilograms. The plank originally at rest is free to slide on a frozen lake, which is a flat, frictionless surface. Okay, so all of this is on ice. The girl begins to walk along the plank at a constant velocity of 1.5 meters per second to the right, relative to the plank. And that's what makes this one a little bit trickier. It's a relative velocity. What is her velocity relative to the surface of the ice, and what is the velocity of the plank relative to the surface of the ice? So V girl relative to the plank is equal to 1.5 meters per second to the right. I'm going to consider right to be the positive direction. Now, what actually happens when this girl starts moving is she exerts a friction force between her foot and the plank, which pushes backwards on the plank, and the plank exerts an equal and opposite reaction friction force to the right on the girl. So friction of the plank on the girl pushes the girl forward, and friction of the girl on the plank pushes the plank backward. The plank being heavier doesn't get pushed back with as much acceleration as the girl gets pushed forward, but they are equal forces acting on both objects. So plank will actually start moving to the left, at least from the perspective of the ground, the ice. And that's what we're trying to find. The girl isn't actually moving at 1.5 meters per second. She's moving at a little bit less than 1.5 meters per second, but because of the plank moving back, it feels as if she's moving at 1.5 meters per second because she is crossing 1.5 meters worth of plank every second. Not just due to her own speed, but also due to the plank pulling and sliding back underneath her. So we can say that this is actually equal to V girl relative to the ice minus V plank relative to the ice. We can say that this is equal to V girl minus V plank relative to the ice. Okay, where does momentum figure into all this? Well, since an equal and opposite amount of force is being exerted between the two, and there are no other forces that are causing a change in momentum for either of these objects, we can say that the momentum is conserved. A lot of people just jump right ahead and assume momentum is conserved, but there's actually a condition for it that needs to be fulfilled. The net external force must be 0. So if we take a look at other forces acting on the plank and the girl, we've got the force of gravity on each of them, and we've got normal forces on each of them. Those are vertical forces, which definitely cancel out because common sense would suggest that the plank and the girl do not accelerate up or down. The only remaining force is the force of friction, which is an internal force because that's a force that the two objects in question exert on each other. Okay, then where do I want to go from here? I'll just do, so momentum initial, when they both started off at rest, that would have been 0, equals momentum final. If net force external equals 0, then change in momentum of the system equals 0, which means momentum final of the system equals momentum initial of the system. Since this is a one-dimensional problem, I'll just use positives and negatives to indicate direction. Positive is to the right, negative is to the left. Final momentum of the system would be m1 v1 final plus m2 v2 final equals initial momentum of the system would be m1 v1 initial plus m2 v2 initial, but we already know both started at rest, so the initial momentum was 0. I'll say that object 1 is the girl and object 2 is the plank. So we're going to say 45 kilograms times v girl plus 150 kilograms times v plank equals 0. That's one equation and two unknowns. We have another equation in those same two unknowns, which is over here. V girl and V plank are just the velocities relative to the ice. So they're the same V girl and V plank mentioned in this equation up here, and since we've got two equations in the same two unknowns, we can solve, as long as one equation is not a multiple of the other, which is clearly not the case. Okay, how do I want to do this? So I guess I will rearrange this. I'm going to solve by substitution. I'm going to have V girl equals, I'm going to add V plank to both sides, equals V plank plus 1.5. Substitute that in here, and we get 45 times V plank plus 1.5 plus 150 V plank equals 0. Distribute the 45, so I get 45 V plank plus 150 V plank is 195 V plank. And then plus 45 times 1.5, I think, is 67.5. Let's double check. Yep, 67.5. Equals 0. Subtract 67.5 and divide by 195. Negative 67.5 over 195 is negative 0.346. I guess I'll keep 3 decimals this time. V Planck relative to the ice is negative 0.346 meters per second. What was the question even asking? So it said, what is her velocity relative to the surface of the ice, and what is the velocity of the Planck relative to the surface of the ice? Okay, so we answered part B before part A. That's fine. This happens all the time in physics. We can just go ahead and solve for V girl next. So all we have to do is add 1.5 to V Planck, which we just discovered. Oh, also I should note that the value we are getting for V Planck makes a lot of sense. For one, it's in the correct direction. It's to the left, as indicated by the fact that it came out negative. And also, it's pretty small in magnitude. It should be smaller in magnitude compared to the velocity of the girl. And the velocity of the girl is close to, but not quite, 1.5. It's 1.5 more than the Planck. So yeah, I would expect V Planck to be pretty small in comparison. Anyway, if I do 1.5 added to V Planck plus 1.5 negative 0.346 plus 1.5 gives me 1.154. So V girl equals 1.154 meters per second. And there we go. That takes care of part A. And then for part B, V Planck is 0.346 meters per second to the left is how I would word it. I would drop the negative and rewrite that as 0.346 meters per second to the left, as shown in the solution steps to part A. If you find the answer to part B along the way to part A, then on your exam, what you would write down is you would copy the answer down and then you would state as found in the previous part, so that you let the grader know that you actually did do the work and let them know where to look for it. Not that they would skip to reading your part B before reading your part A, but you know, just for the sake of being safe. Actually, it might be possible, depending on how they go about grading it. I could see a scenario where, in the interest of fairness, they have like one grader grade your part A and then another grader looks at your part B. I feel like it would be better to just have both graders look at all parts of your solution instead, but I don't know exactly how they go about grading. So just cover all your bases to be on the safe side. If you solve for a later part in a previous part, then just make sure to state that your solution steps were shown in that previous part so that you have yourself covered and don't lose points for not showing your work. Okay, that takes care of problem 21 from my book. Where do I want to go next? This one says we've got Ooh. Yeah, this one might be worth looking at. So I'll go ahead and give the initial drawing over here before bringing out a new sheet. So it says a 65 kilogram person throws a .045 kilogram snowball forward with a ground speed of 30 meters per second. A second person with a mass of 60 kilograms catches the snowball. Both people are on skates. The first person is initially moving forward with a speed of 2.5 meters per second, and the second person is initially at rest. What are the velocities of the two people after the snowball is exchanged? Disregard friction between the skates and the ice. Okay, so we've got person 1 with a snowball in hand, moving forward at some sort of velocity. The second person was initially at rest. So that would be, I guess, scene 1. Scene 2, the first person, I would imagine they're still moving forward, although a little bit slower after having thrown the snowball. The snowball is in the air, and this person is still at rest. And then scene 3, first person is still at the same speed they were after releasing the snowball. Snowball gets caught by person 2, who now starts moving in the direction that the snowball was coming at them. So yeah, 3 different scenes to consider. Well, of course, this is going to be a conservation of momentum problem because it's in the conservation of momentum section of the momentum chapter of my textbook, but we still need to justify it. Is the net force external equal to 0 in I guess the 2 collisions that are happening here? If they're both on skates and on the ice, there's no friction to worry about, so we don't have to worry about friction as an external force. The force of gravity and the normal force on each of them is going to cancel out. Technically, the gravity is going to affect the snowball. Technically, there's a net external force on the snowball, which is gravity, so its momentum isn't entirely conserved, but the horizontal momentum at least is conserved. So momentum isn't conserved for the snowball vertically, but horizontally there's no external forces acting on it. The only horizontal forces acting on the snowball are the force that the first person exerts on the snowball, but it exerts an equal amount of force back, so net force external on the system of person A and the snowball would be 0 in that case. That horizontal force they exert on each other is internal. And similar thing going on when the second person, person B, catches the snowball. Same idea there. Those horizontal forces form an equal and opposite action and reaction pair, so whatever change in momentum is exerted on the snowball, an equal and opposite change in momentum is exerted on the person horizontally, so the total horizontal momentum change is 0 across both of them. So yeah, horizontally, momentum is conserved. Net force external in the x direction at the very least is 0. In the y direction, gravity is going to have a little bit of an effect on the snowball, but we're assuming this snowball reaches the second person fast enough that it doesn't drop to the ground or really change in height all that significantly. So it's probably not a lot of change in momentum anyway, and even if it was, it's in the y direction. And we don't have to worry about anything happening in the y direction here. Okay, I might actually be able to fit something onto this page before moving on to another one. Let's see how many of these calculations I can do. So first with person A, we've got the mass of the first person is 65 kilograms. 65 kilograms. The second person is 60 kilograms. 60 kilograms. And the snowball is 0.045, yeah, 0.045 kilograms. And we know the initial velocity of the person is 2.5 meters per second. 2.5 meters per second. And we also know that the snowball is thrown forward with a ground speed of 30 meters per second. Which color do I want to use here? Let's try and make do with yellow. I don't like this yellow marker. I'm sure I've expressed that multiple times by now, which is part of the reason I'm choosing it, so it can die quickly. Okay. Between here and here, I'm just looking at an interaction between person 1, or person A if you want to call them that, and the snowball. So I've got 65 kilograms times 2.5 meters per second plus 0.045 kilograms times the same 2.5 meters per second. That was the initial momentum of person 1 and the snowball, equals their final momentum, which is 65 times, well, we don't know yet. I guess I'll call it a V1 final, plus the snowball is 0.045 again, times it moved at 30 meters per second after being thrown. Okay, easy enough, just solve for V1 final, so let's go ahead and multiply things out. I can factor out the 2.5 here and just do 2.5 times the sum in parentheses of 65 plus 0.045, so 65.045. They made that really easy for us. And then subtract 0.045 times 30. Okay, so this was 162.6125, and after I subtract 0.045 times 30, I'm left with 161.2625. 161.2625 equals, let me wall this off, equals 65 times V1 final If I divide by 65, I get about 2.48. So barely even slowed down. I'm getting V1 final equals 2.48 meters per second. They barely even got slowed down by that, which I guess isn't a surprise considering that this person's mass is what, about 20 times as much as the mass of the snowball, give or take. Yeah, 20 times the mass. I can see why you don't get that big of a change in your velocity. Okay, so that's the first collision, or I guess backwards collision if you think about it, from here to here. Now we want to look from here to here. What happens? And this is going to require a new sheet of paper. So we have a snowball at 30 meters per second collides with a person at rest. The snowball has 0.045 kilograms of mass and the person at rest has 60. So we can do momentum initial is 0.045 times 30 plus 60 times 0 equals momentum final, which is 0.045 times V2 final plus 60 times also V2 final, since the second person and the snowball must move together after the snowball is caught. And is it justified to use this? Is the net force external still 0? Yeah, we already discussed that earlier. When the person catches the snowball, they exert a horizontal force on it to the left. The snowball exerts a force on them to the right. In response, the magnitude of that force is the same for both of them. The amount of time they're in contact with each other must be the same, because that's just common sense. You can't touch something for 3 seconds while having that thing only touch you for 2 seconds. It doesn't work that way. Either you're both touching at the same time or you're not. So the F's are the same, the delta T's are the same, the only difference is in their directions. So whatever momentum change you get for the snowball, an equal and opposite momentum change occurs with the person, and so the total momentum change is 0. I know I probably sound like a broken record repeating that, but I think it bears repeating. If all we care about is just getting to the problem and plugging in numbers, then we're not really learning physics, are we? Anyway, put these together since we can factor out V2 final, and that gives me 60.045 times V2 final. 60.045 V2 final equals whatever this is. That's going to be 0.045 times 30 is 1.35. And if I do 1.35 divided by 60.045, I get 0.0225. V2 final is 0.0225 meters per second. What to do next? That one might be worth looking at, but I think I'll save it for later. How about a ballistic pendulum problem? If you're one of my students, then you probably got this one from me as homework. Either this one or the other one that I'm looking at. But even so, it may have been a while since you last saw it, so it can still serve as good practice even if it is a repeat problem. Let's see. A 7-gram bullet is fired into a 1.5 kilogram ballistic pendulum. The bullet emerges from the block with a speed of 200 meters per second, and the block rises to a maximum height of 12 centimeters. Find the initial speed of the bullet. So I guess I'll draw it over here. So this thing is 7 grams, or 0.007 in kilograms. And it has some unknown initial speed. I'll call it V. I don't want to use B, because B for bullet and B for block, that's going to be confusing. What should I call it instead? Yeah, I'll call it V-Bull. Yeah. Watch somebody walk in on this meeting and question why I've drawn a bull in this weird shape. I mean, it would be nice to actually have that as a book problem. It would be nice to have a book problem where, you know, a matador is struck by a bull and we'd have to calculate just how strong the force of collision is and justify why that stuff is dangerous and you probably shouldn't do it. Although you don't really need physics to know that being rammed by a bull is dangerous. Anyway, 1.5 kilogram ballistic pendulum. It's going to be tied by a string to some platform of sorts. And the bullet emerges from the block with a speed of 200 meters per second. So sometime later, the bullet comes out of the block at 200 meters per second, and the block rises to a maximum height of 12 centimeters. Now, does the bullet emerge immediately before the block rises, or when it's on its way up, or just as it reaches its maximum height? Turns out that doesn't really matter. Turns out that doesn't really matter because the energy transferred to the block is the same regardless of when it happens. I guess it would make a difference if the block rose to some sort of maximum height, then started dropping down, and then the bullet emerged. If that was the case, then I could see that kind of messing with this problem a little bit, and, well, maybe more than a little bit. It would make our calculations pretty much impossible, as far as I can tell. Actually, let me think about this for a second. So, well, actually, if the block reached its maximum height while the bullet was still in it, then they wouldn't have even mentioned the bullet emerging from the block. We would just consider the bullet and block both rising to that maximum height, and we'd calculate based off of that. We wouldn't even have to consider how fast the bullet is moving after it emerges. Although I guess it would give us a little bit of a concern about how fast the bullet was moving inside the block once the block reached that maximum height. Because for the bullet to emerge from the block, it would have to move at a different speed than the block. For two objects to separate from each other, their velocities have to be different. But I guess in that case you could argue that since the bullet has such little mass, that its kinetic energy could be assumed to be... Well, no, because if it emerges at 200 meters per second, that's still a lot of kinetic energy because you have to square it. Yeah, I guess it would get really, really messy if the bullet was still moving within the block even after the block reached maximum height. But there's no way they would give you something that complicated in this textbook. At least not without giving you some more information, because otherwise you wouldn't be able to do any math with it. So yeah, here, just from the fact that they tell us that the bullet emerges in the first place, it would have to have emerged by no later than the moment that the block reaches its maximum height. And as long as it leaves the block between the time that the block starts rising and the time that the block reaches its maximum height, there should be no difference energy-wise in how much energy the block gained. Because the block gaining the energy, I know I'm probably getting way too deep into this, but the block gaining energy happens as long as it's in contact with the bullet. So if you assume that the block gains all this kinetic energy like in an instant and then starts rising, versus it gains that kinetic energy while it's rising, if it's gaining the same amount of kinetic energy either way, then the total mechanical energy of the block by the time it's done rising, it'll be the same either way, whether it was gained all in one instant or gained along the way up. It won't change what your final potential energy is when you reach the maximum height. So yeah, the math will work out the same. Okay, so that's a little, I guess, philosophical tangent out of the way. Well, I wouldn't call it philosophical, but now I'm just nitpicking my words and going off on another tangent. So let's abandon that and actually go back to solving this problem. So the block starts at rest, because that's just how a ballistic pendulum is supposed to work. Bullet hits it, so that's going to be a collision step, and then after the collision, the bullet, we can treat it as if it emerges right away. Again, I just got done explaining that it doesn't matter if it emerges right away or somewhere along the way or at the end, as long as it emerges by some point between when the block starts to rise and when it finishes rising. Let's say that the bullet passes through and emerges, and I know I probably should draw a hole through this block, but let's pretend that the hole is in the block, in the part of the block that's like behind the page. If I made this a more three-dimensional drawing, I guess the hole in the block would be somewhere like there. So bullet hits the block, bullet exits the block now has some sort of kinetic energy, and the block rises. And by this point the bullet is long gone. The bullet emerges at, they said, 200 meters per second. And now the block is at some height above where it used to be. There's going to be some sort of change in height over here due to that kinetic energy converting to potential energy. Okay, so let's go ahead and see what numbers they gave us apart from the 200 meters per second. The bullet was 0.007 grams. Oh, wait a minute. I was looking at the wrong problem. Okay, we already have that data, and that, and that. And the block rises to a maximum height of 12 centimeters. I'm going to rewrite that as 0.12 meters. 0.12 meters. And yeah, find the initial speed of the bullet. So let's go ahead and plug in numbers into our equations. Well, before that, let's justify the use of our equations. So between here and here, can we assume that momentum is conserved? At least in the horizontal direction. Horizontally, the only forces acting on the bullet and the block during the collision are the forces that the bullet and block exert on each other. So, yeah, net force external in the x direction is 0, and in the y direction, technically gravity is going to have an effect on this bullet. It'll gain some vertical momentum downward. But we are not going to concern ourselves with that. We'll assume that the bullet moves fast enough that there's not enough time for the momentum gained due to gravity to have any measurable effect on our ballistic pendulum. So technically, momentum is not entirely conserved, but it's approximately conserved. So we can justify using conservation of momentum there. Can we justify using conservation of energy then after the block begins to rise and between the point where it begins to rise and reaches its maximum height? That would require the total non-conservative work to be 0. So is it 0? Well, the forces acting on the block are the force of gravity, which is conservative, and the tension force in the string, which is not conservative, but the tension force in the string will do 0 work because as this object swings, the direction of the tension force is going to be perpendicular to the way that the block moves. When the block is at the bottom, it will be moving horizontally to the right at first while the rope is pointing vertically up. Then as it swings, I guess I'll draw it over here. So when the block is here, tension is up, but displacement is to the right. Then sometime later, say over here, tension is this way, but displacement is going to be in that direction. And once it reaches its maximum height, technically there's no displacement going on, but if there was, it would be going in that direction while the tension is in that direction. So the tension is always perpendicular to the direction of displacement. The direction of tension and the direction of displacement change by the same number of degrees in the same amount of time, so they always stay perpendicular to each other. And if the force and displacement are perpendicular, we know that the work done by that force must be zero. So we do have a non-conservative force, but it does no work, so our non-conservative work is indeed zero. We can justify using conservation of mechanical energy. Alright, so let's go ahead and write out our momentum step first and then our energy step. So conservation of momentum would tell us V bullet times M bullet. So V bullet, I guess V bullet initial would be more precise, times the mass of the bullet, which is 0.007, plus 1.5 times 0 is equal to 0.007 times V bullet final, which is 200, plus 1.5 kilograms times, I'll call it V block initial, V block initial. And I think, wait, can we solve this? No, because we've got two unknowns. Okay, so we can't solve that yet, so no problem, we'll just continue. Then from here to here we've got a conservation of energy problem, so I'll do that in pink. We have, there's going to be some sort of initial kinetic energy here, 1.5, or 1/2 I should say, times the mass is 1.5 times V block initial squared, plus 0 gravitational potential energy. I'm deciding that this is my 0 line right here. So plus 0 gravitational potential energy equals, there's going to be no kinetic energy at the top, it'll come to rest, plus all the gravitational potential energy, so that's 1.5 times 9.8 times h, which is 0.12. And the 1.5 cancels out. The mass of the block was not even needed, at least for this part. We can multiply the 2 over and take the square root, so V block initial is equal to the square root of, let's see, 2 times 9.8 is 19.6 times 0.12. And then let's grab the calculator and see what that amounts to. Square root of 19.6 times 0.12, and I'm getting about 1.53. Getting about 1.53 meters per second. And now that I know this, I can go back and plug it in here. And I can solve for the initial speed of the bullet. So let's do 0.007 times 200 plus 1.5 times 1.53 is 3.695. Let's switch colors. So I get 3.695 on the right-hand side of this equation equals 0.007 V bullet, 0.007 V bullet. And if I divide by 0.007, I get, it better be more than 200. Divide by 0.007, and I get 527.86, which is pretty reasonable for the speed of a bullet. V bullet equals 527.86 meters per second. If it came out less than 200, then that would have been a pretty good indication that a mistake was made somewhere along the way. It's always good to make some small predictions about your numbers. Will they be more than or less than some other number mentioned in the problem? And how do you know? If you can make those sorts of predictions, you can get better at catching mistakes if a number seems off. Then again, sometimes in physics you get numbers that look too big but are actually completely legitimate, and other times you get numbers that seem too small but are again completely legitimate, because physics is not always that intuitive. But no harm in doing a double take when something looks like it isn't coming out to the number that you would reasonably expect. That takes care of the bullet fired into the ballistic pendulum. Let's see what else we can do around here. Let's go ahead and do an example of elastic collision where both of your final velocities are unknown. And I'll actually go over a derivation that I have shown to my students, but it bears going over again. It bears repeating. I know a lot of teachers just give you the result of this derivation without actually showing you how to do it, which is a shame. It's a big problem in math and science courses where they just give you formulas to use without fully justifying them. Sometimes it's because there's just genuinely it's just genuinely difficult to prove with the math that you currently have, and other times it's just being pressed for time because that's what our crazy education system demands, and other times it's really just laziness. So I don't know what to make of it, but regardless of the reason, I don't like it. Anyway, the problem says we've got a 10-gram object moving to the right at 20 centimeters per second. It makes an elastic head-on collision with a 15-gram object moving in the opposite direction at 30 centimeters per second. Find the velocity of each object after the collision. Well, since both of the masses are in grams and both of the initial velocities are in centimeters per second, I can actually skip on converting here. I don't have to convert to kilograms and meters per second. All that means is that my final velocities will come out in centimeters per second. If I put grams in everywhere and I put centimeters per second in everywhere, then I should get centimeters per second out. So yeah, 10 gram object moving to the right at 20 centimeters per second. Let's say there are blocks on a frictionless table, for example. So this thing is, I probably should have drawn it bigger. 10 grams moving to the right at 20 centimeters per second. Makes an elastic, not inelastic, an elastic, A-N. Gotta be very careful with those terms. Makes an elastic head-on collision with a 15 gram object moving in the opposite direction at 30 centimeters per second. So 15 gram object moving at 30 centimeters per second in the opposite direction. Find the velocity of each object after the collision. We are told this collision is elastic. What does that mean? It does not mean that the objects bounce off of each other. I mean, they will, but that's not what defines elasticity. Elastic versus inelastic is not defined by bouncing versus sticking. Elastic versus inelastic is defined by whether or not energy is conserved in the collision. Elastic collisions are the collisions where energy is conserved. You can have plenty of inelastic collisions where the objects bounce. If the objects stick, that's pretty much guaranteed to be inelastic. That's pretty much guaranteed to be accompanied by a loss of energy, but you can still have a loss of energy if the objects bounce off of each other, so be very careful about that. Elastic versus inelastic is not defined by bounce versus stick. That is a common misconception. I see it all the time, and it's not good. It's not good at all. Elastic collisions are collisions in which energy is conserved. Over here, there's no change in height, so we don't have to worry about potential energy. So the only energy to take into account is kinetic energy. Kinetic energy initial equals kinetic energy final. 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared equals 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. Is that clear on the screen? I've noticed while looking back at the videos that for some reason the right-hand side of the page seems to be a little bit less focused than the left-hand side of the page. But hopefully with my voice it's clear enough what I'm writing, because I do try to explain what I'm writing as I write. We can cancel the 1/2 everywhere, by the way, so we don't even need the 1/2 in this. And then, of course, we've got conservation of momentum going on. So, conservation of momentum can be justified because the gravity and normal force are just going to cancel each other out, so the net force due to those is 0 in the vertical direction, and in the horizontal direction the only force we have is forces that the blocks exert on each other. If the blocks are considered to be our system, then forces that one part of the system exerts on another part of the system is an internal force, not an external force. So yes, net force external here is 0. We're assuming, of course, they're moving on a frictionless surface. Well, it doesn't mention the frictionless surface, but we can assume that to be the case. Or at the very least, we can assume that during the moment of collision, even if there was friction, in the moment of collision, friction doesn't have enough time to do anything to add or remove. Well, I guess friction could only remove momentum from the system. Alright, so with that justification made, we can write m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. Now I could start plugging in numbers, but instead I want to do the derivation that I was just talking about. So let's see what we can do with these two equations. This is going to require a little bit of, well, maybe not just a little bit, of clever algebra. So we need to find some sort of simplification for this. You could go ahead and use these two equations together to solve for your two unknowns, v1 final and v2 final, but if you do a little bit of work here, then you can derive a much simpler equation that doesn't involve all these squares, which is great because getting a second equation that is linear instead of quadratic would reduce your chances of having to solve a quadratic formula. So let's see what I can do here. First off, I want to group my terms by mass. So what I want to do is I want to get all of the m1 terms on the left and all of the m2 terms on the right, for example, or vice versa. So yeah, I'll do m1 on left and m2 on the right. So m1 v1 initial squared, I'm going to have to subtract m1 v1 final squared. So m1 v1 initial squared minus m1 v1 final squared. So that's subtracting that over to the left, and I'm going to subtract this over to the right. So equals m2 v2 final squared minus m2 v2 initial squared. m2 v2 initial squared. Okay, so that's rearranging the first equation. Let's rearrange the second equation in a similar manner. Subtract m1 v1 final over to the left and subtract m2 v2 initial over to the right. So m1 v1 initial minus m1 v1 final equals m2 v2 initial minus, or no, final I should say, m2 v2 final minus m2 v2 initial minus m2 v2 initial. Okay, from here I can factor out m1 on the left-hand side and m2 on the right-hand side for each equation. So let's switch colors again. I want to do a lot of color switching here just to keep everything in order, just to keep everything organized. So if I factor out m1, I get v1 initial squared minus v1 final squared in the parentheses equals, if I factor out the m2, I get v2 final squared minus v2 initial squared. And then for the second equation, I get m1 times v1 initial minus v1 final equals, if I factor out the M2 for the second equation, I get V2 final minus V2 initial on that right-hand side. Okay, so what was the point of doing this? The point of doing this was to eliminate the mass. I can now eliminate the mass because even though your algebra class taught you that you can add and subtract equations with each other, you can also divide and multiply equations. I can take this equation divided by this equation and still get a valid equality out of that. This stuff divided by this stuff equals this stuff divided by this stuff. It makes sense when you think about it. If this is equal to this and this is equal to this, then this divided by this must be equal to this divided by this. It makes sense, just give it some thought. So if I do that division, then the mass is going to cancel out, and let me switch colors again. The mass is going to cancel out, and I will be left with V1 initial squared minus V1 final squared over, let me not include that equal sign just yet, over V1 initial minus V1 final equals V2 final squared minus V2 initial squared over V2 final minus V2 initial. Some of you can probably guess what the next move is going to be. These numerators are differences of squares. I can factor these. I'll continue that up here. I probably should have started this whole thing further to the left, but that's just the way I do things, I guess. So I can continue this up here, and I'll do yet another color switch. Let's do the lavender color this time. So this is going to become V1 initial minus V1 final times V1 initial plus V1 final over V1 initial minus V1 final equals, over here we're going to have V2 final minus V2 initial times V2 final plus V2 initial all over V2 final minus V2 initial. We can cancel the minuses. We can cancel V1 initial minus V1 final with that denominator, and we can do the same thing over here. And that leaves us with V1 initial plus V1 final equals V2 final plus V2 initial. I want to rearrange this, so I'm going to subtract V2 initial and subtract V1 final on both sides, and that gives me V1 initial minus V2 initial equals V2 final minus V1 final, which I can rewrite one more time as V1 initial minus V2 initial is equal to the negative of, and then I'm going to rearrange the subtraction here. I'll make it V1 final minus V2 final. At least this is the way that I prefer to write it. So this relationship holds true for collisions that are elastic. V1 initial minus V2 initial equals negative V1 final minus V2 final. But that's kind of hard to remember because, you know, you could easily screw up. Is it V1 first or is it V2 first? And is it initial first or is it final first? It's very easy to get mixed up here and forget the formula unless we can come up with some sort of meaning to it that's easier to remember. And there actually is a meaning to this result. It's relative velocity before and after collision. V1 initial minus V2 initial is the difference in velocity between these things is the velocity of object 1 relative to object 2. And V1 final minus V2 final would be the velocity of object 1 relative to object 2 after collision. So let's actually go ahead and calculate this. V1 initial minus V2 initial, 20 minus negative 30 is 50 centimeters per second. You can think of this as the rate at which the distance between these two objects is closing. So the rate at which the gap between them is closing equals negative this rate equals the negative of the rate at which the gap between them will start expanding after they collide. So they're coming at each other at 50 centimeters per second, essentially, before collision. After collision, they're going to be separating from each other at a rate of 50 centimeters per second. The distance shrinks at a rate of 50 per second, and then after collision it grows at 50 centimeters per second. That's essentially what this is telling you. Relative velocity before collision equals the negative of the relative velocity after collision, and then just pick one object that you're defining velocity relative to. It could be the first object or the second object. It doesn't matter as long as you stick with that same object for before and after. So now that we have this, we can use this as our second equation with our conservation of momentum equation, and that will give us two linear equations where the final velocities are unknown, which is going to be a lot more straightforward to solve than if you had to combine the conservation of momentum equation with this. This would have given you more trouble, especially if you don't pay too much attention when solving your quadratic and you end up picking the wrong root out of the two possible roots that you might have to choose from. This eliminates the guesswork out of it. So that's another benefit to knowing this formula. But I would say the most important thing of all is just having the algebra skills to be able to derive this formula in the first place. I know they're probably not going to test you on this, but if you care about your physics, you probably should test yourself on this. Because, physics is one of the best things about physics courses is that they challenge your math skills to the point where you might become a better mathematician studying physics than if you actually studied math. But now I'm rambling, so let's get back to solving the actual problem. If I go ahead and, well, I don't have enough room to write anything in here, so let me go ahead and grab a new sheet of paper. if I do my conservation of momentum equation, m1 v1 initial plus m2 v2 initial, so 10 grams times 20 centimeters per second plus 15 grams times negative 30 centimeters per second. So 10, I'll write the units this time, 10 grams times 20 centimeters per second plus 15 grams times negative 30 centimeters per second equals 10 grams times wait, I drew my parentheses wrong. 10 grams times V1 final plus 15 grams times V2 final. And then we have our relative velocity equation, V1 initial minus V2 initial. So that's 20 centimeters per second minus negative 30 centimeters per second equals negative V1 final minus V2 final. Alright, let's see why we can get away with just using the units that they gave us this time around. Well, I can divide everything by grams, so we can already see that the grams are canceling out. And if the grams are canceling out and you're putting centimeters per second in, then it follows that the only thing you could possibly get out of this is centimeters per second. And same goes for the second equation. If only centimeters per second are going in, then centimeters per second have to be what comes out. So that's that question fully addressed, in case you weren't convinced by what I said before. Okay, 10 times 20 is 200. 15 times 30 is negative 450. Equals 10 V1 final plus 15 V2 final. And over here we've just got 50, or I guess if I move the negative sign over to the left, I'll say negative 50 equals V1 final minus V2 final. Add V2 final over to the left-hand side, and we've got a really simple substitution that we can make. V1 final is equal to V2 final minus 50. And then plug that into here, or I guess here, and we should be good to go. Let's see, 200 minus 450 is negative 250, equals 10 times V1 final was V2 final minus 50, plus 15 V2 final. Okay, distribute the 10 V2 final plus 15. V2 final is 25 V2 final. So 25 V2 final. And then 10 times negative 50 is negative 500. Add 500 to both sides. That gives us positive 250 equals 25 V2 final. So V2 final comes out to, if I divide by 25 on both sides, V2 final comes out to positive 10 centimeters per second. Does that make sense? For this thing to be going at positive 10 centimeters per second to the right. Well, going to the right isn't unexpected. The 15 grams is a little bit heavier, so it's not guaranteed to go to the right after collision. It could very well continue going to the left at a lower speed, but being bounced back hard enough that it actually starts going to the right is not completely unheard of. Especially with 10 centimeters per second, that's low enough that it's still believable. Now let's see if we get something that makes sense for the 10 gram block. So if I just plug back into here, 10 centimeters per second minus 50 centimeters per second, that just gives me negative 40. And that's in centimeters per second. Does it make sense for the lighter block to be bounced back to the left? Yeah, that makes sense to me. I'm not surprised by that, especially given that it's lighter and that it collided with something that was not only heavier but also faster. Yeah, there's more momentum overall to the left than to the right, and if the second block is going to be moving to the right, then the first block better be moving to the left and fairly quickly so that the total momentum is still to the left. So that still makes sense to me. And if we go back and plug the numbers into this equation, 10 times negative 40 is negative 400 plus 15 times 10, 150, negative 400. That is indeed the negative 250 that I got before. So yeah, it all checks out. And that takes care of a, what do you call it? A problem with two unknown final velocities. An elastic collision problem with two unknown final velocities. So, again, practice this derivation. I mean, on your big test, you're not going to have the time to do all this, but still practice it anyway. And then for the test, yeah, just remember this result, but know where it comes from, so that you don't use it in situations where it doesn't actually apply. That's my rule for shortcuts. You can use them if you can prove them and understand what their conditions are. I've seen a lot of people try to use shortcuts that they just found on the internet somewhere, and they end up using those shortcuts in the wrong places at the wrong times and end up regretting it later. Don't be one of those people. Let's take a look and see if I can find one more problem to wrap things up for tonight. That's a simple inelastic collision problem. I don't want to do that one. I guess one of the negatives of this sort of improvisational style is that you have to deal with these sort of awkward long pauses as I search for problems that might be interesting enough to solve. Okay, I think I'd like to give this one a try. So it says we have two carts of equal mass, 0.25 kilograms. They're placed on a frictionless track that has a light spring of force constant 50 newtons per meter. Let me actually draw the situation before going any further, so that you know what I'm talking about. So we have a spring over here, supported by a wall, and then we've got two blocks, each of the same mass, and they're on a frictionless track. The mass of each block is 0.25 kilograms, and the spring constant is 50 newtons per meter. It says the red cart, which in their drawing, the red cart is the one on the left. So the cart on the left is given an initial velocity of 3 meters per second to the right. 3 meters per second to the right. And the blue cart is initially at rest. If the carts collide elastically, find the velocity of the carts just after the first collision and find the maximum compression of the spring. So how far does the spring get compressed after the second block collides into it? So I guess the way it's going to happen is first block is going to collide with the second block will gain some momentum to the right, it will bump into the spring and transfer energy to that spring. And yeah, it says find the velocity of the carts just after the first collision and the maximum compression of the spring given that the collision is elastic. Given that the collision is elastic, that means energy is conserved in the collision, which means we don't even have to do the momentum step to answer part B. We can figure out how far the spring gets compressed. Oh, wait, actually, yes, we do have to do the collision step, because if some of the kinetic energy remains with that first block, then not all of it is going to get converted into potential energy. Okay, I was getting ahead of myself. I was about to jump to the conclusion that since the energy is conserved in the collision, the initial energy of the first block is just going to equal the elastic potential energy when the spring is fully compressed, but no, that's not true, because that energy might not all reach the spring in the first place. I'm wagering that it will, because I'm guessing that in the collision, all the energy is just going to transfer to the second block anyway, but let's do our math and check if my intuition is right. Let's do the math and see if my intuition is correct on this. So we already know our formulas. So the track is frictionless. Normal force and gravity on the blocks cancel each other out, so those external forces net out to zero. The only other force during the collision is the force of the blocks on each other. That's an internal force, so net force external during this collision is zero. We can justify using conservation of momentum here. So we can say m times 3 plus m times 0 equals m times, I guess we'll call it V1 final, plus m times V2 final. Oh, would you look at that, since the masses are the same, the mass cancels out. So 3 equals V1 final plus V2 final. We also know from what we derived earlier that this relationship must be true, V1 initial minus V2 initial, so I guess in my case that's going to be 3 minus 0 is equal to negative V1 final minus V2 final, so 3 minus 0 equals negative of V1 final minus V2 final. Or in other words, if I move the negative over to the left-hand side, negative 3 equals V1 final minus V2 final. Okay, so actually what I can do here is I can just add this equation to this equation. I can actually solve this by elimination. I don't even need substitution this time. So let's go for gray. If 3 equals V1 final plus V2 final, and I add that to negative 3 equals V1 final minus V2 final, 3 plus negative 3 is 0, equals V1 final plus V1 final is 2 V1 final, and V2 final minus V2 final is gone, so V1 final is equal to 0. So I guess my intuition was correct. All of the momentum simply transfers to that second block. If V1 final is 0, we can plug that back into either one of these equations and solve for V2 final is equal to 3. V2 final must then be equal to 3. Positive 3, meaning it will indeed be to the right, and that agrees with our common sense. You don't bump into something at rest and see it move opposite to the direction it was bumped into. That just doesn't happen in real life. So we already knew the direction was supposed to be to the right. And now we can do the second step, which is this block moving at 3 meters per second, compressing the spring. It will have a kinetic energy of 1/2 of its mass, which was 0.25 kilograms. Now we actually need that value, times its velocity squared, so times 3 squared. Plus, initially the spring is uncompressed and there's no gravitational potential energy, so plus no potential energy initially, equals, at the end, once the spring is fully compressed, the block will have come to a stop, so 0 kinetic energy plus there's no gravitational potential energy here to take into account, and that leaves us with all elastic or spring potential energy, 1/2 times kx squared, k being 50. Solve for x, we can cancel the 1/2 on both sides. And let's see, 0.25 times 9 divided by 50. Actually, if I divide by 50 first, let's see, 0.25 over 50, well, 25 over 50 is 1/2. So 0.25 over 50 is 1/200th, if I'm not mistaken. I'll just use the calculator for this. It's been a long day. My brain isn't fully functional. 0.005. Yeah, that's a 200th. 5 out of 1,000. Okay, so my brain is functioning better than I thought. 0.005 times 9 equals x squared. And if I go ahead and multiply that out, multiply by 9, and take the square root, and I'm getting x equals 0.212132, so I'll just say 0.212. I'll say x is approximately 0.212, and that should be in meters because I plugged in kilograms and newtons per meter, so yeah, that should come out in meters. And there we go. I mean, I was expecting it to be quick, but this is even quicker than what I was expecting. I guess that's one skill that I still have to improve on, predicting how long a problem will actually take. If I got better at that, I'm sure my students would rejoice because I wouldn't hold them for an extra 5 to 10 minutes to finish up a problem. Do I have anything else I want to say before wrapping things up? Let me see. So, especially for AP Physics students, do I have any important messages? Well, the AP Physics exams are going to be in the second week of May. So you've still got about, how many weeks is that? Let me check the calendar. You've got 1, 2, yeah, we've got 3 more of these office hours sessions that we can fit in before the AP exam. So if anybody has any requests, make sure to come in and make those requests. Make sure to come in and ask your questions. If not, then I'll just continue doing this, going topic by topic and just choosing whatever problems I think might be helpful as review. And I am thinking of doing just like a marathon AP Physics 1 stream. I'm still planning things out for that, so it's not set in stone yet, but if I can make it work, then I will try to do that. I'll be streaming that on YouTube, not on Twitch. I feel like I'd be able to get more eyes on it there. And that was the plan from the very beginning, so yeah, not related to what I said at the beginning of this stream about maybe quitting Twitch for YouTube, but yeah, we'll see. If I can get that whole marathon stream planned out just the way I like it, then I will go for it. It'll probably be like a 10-hour thing, but it's still in the sort of idea phase. I'm still trying to figure out exactly when and how I want to do it. Plus, I kind of want to do something a little special for it if I'm going to be doing it anyway. And I'm trying to come up with, well, I guess I can tell you, I'm trying to come up with a problem that is very multi-concept, just as a sort of finishing problem for that stream if it ever happens. If not, then maybe I'll do it next year. We'll see. But yeah, that's all the comments that I have. If I remember anything else, then I'll either mention it next time or put it in a pinned comment under the YouTube upload for this video, or whatever the case may be. I'll announce it somewhere if there's anything to announce. And yeah, that'll be it. So hopefully this has been helpful. Have yourselves a good night or day whenever you might be watching this, and take care and look forward to the next one.